Hi everyone. In this section, we are going to talk about the chemical properties of ethers. We are studying the chemical properties, means the chemical reactions. Okay, the first reaction that we'll be taking is the cleavage of carbon-oxygen bond. Okay. First of all, if we look at the ethers, they are relatively inert compounds, means they are less reactive, or we can say in normal conditions they are not reactive. Okay, that's what we mean by the inert. So they are inert compounds, they don't show reactions in the normal conditions, but under drastic conditions we can make them to react. Okay, we can make them to react. So they're stable to bases if we add them with the bases, with the dilute acids, catalytic hydrogenation, and to most other reducing agents. They are very stable. Okay, they are not that much reactive. That's why the functional group that's present in the ethers, okay, that does not contain any active site in their molecule. Okay, this doesn't have any active site in its molecule for the reaction, as we have in the case of hydroxyl group. Okay, similarly in the case of we have the phenols. Even though the oxygen is present in both of these, we can say OH group, and as well as the in the alcoholic group, as well as in the ether group, oxygen is present in both of these functional groups. But under specific conditions, we can make these ethers to react. Okay, under specific conditions, ethers can undergo certain reactions. So if we as these compounds, as we are saying, these are inert, so they have good solvent properties. That is, many of these ethers, they are used as solvents in many different reactions. Why? Because they are inert in these particular reactions. So they show good solvent properties for many non-polar organic compounds. Okay, as it has strong dissolving property as well as low reactivity. Therefore ethers are considered as good solvents in which we can perform different reactions. So there are two, we can consider two reaction sites that are present in what we call as the ethers. One is the molecule, one is the carbon hydrogen bond. If we can do any type of reaction that is with this carbon hydrogen bond that is present in the alkyl group, okay, attached to the ether, and another is this particular oxygen, that is the ethereal oxygen. Okay, you can call it as the ethereal oxygen. This ethereal oxygen can be made reactive. So there are these two sites are reactive. Okay, which we can make reactive towards particular reactions. So in some specific conditions, the ethers can be reacted. They show some reactions. So one of the most popular and the common reaction is the CO bond cleavage. Okay, as since the general formula ether is ROR. Okay, so this R is any alkyl group, okay, or aryl group. Any of these can be aryl groups or alkyl groups, as we have already seen. So here we have a bond between the carbon and the oxygen. Okay, carbon of this alkyl group and this oxygen. Similarly, we have a bond between the carbon and the oxygen, carbon of this alkyl group and the oxygen. Okay, so this bond can be cleaved, and this cleavage of this carbon oxygen bond is the most common reactions. Okay, and this is actually the acid catalyzed reaction in presence of strong acids only. Okay, we cannot use weak acids or dilute acids. We have to use concentrated strong acids to perform this reaction. So this cleavage of CO bond takes place under these drastic conditions with excess of hydrogen halides that actually act as an acid. Okay, these are the halogen acids. halides. We can have any HX, we can have HCl, we can have HBr or hydrogen iodide. These can be any of the hydrogen halides. So as we already do this, the reaction is the acid catalyzed reaction, and we should remember this is the most common and the popular reaction that these ethers show. So the reaction of dialkyl ether with hydrogen halide gives two alkyl halide molecules. If we react the, if we have the dialkyl ether and we take the hydrogen halide, and actually we have to take this hydrogen halide in excess, then we can obtain two alkyl halide molecules, and if this is in excess, we can see. Now, how does this reaction occur? The reaction may occur via Sn1 or E1 mechanisms for 3-degree alkyl groups. Okay, because we have, with this ether we have R groups attached to this. We can have a primary, secondary or tertiary R groups from both the sides or from one side. If it is the tertiary alkyl groups, then it can undergo, mostly it undergoes Sn1 reaction, but even possibility is also, means elimination reaction is also possible. But if there is for Sn2 mechanism, we are following, we have primary alkyl groups. If there is presence of primary alkyl groups that are present in this ether, then the mechanism that is going to follow is Sn2 mechanism. And for secondary alkyl halides, if secondary alkyl halides attached to the ethereal oxygen, then the mechanism depends on the type of solvent that we use, that we will see in the subsequent slides. Okay, so this is the common reaction that we are showing. In this reaction, we have an ether is reacting with a hydrogen halide, and in the reaction the product is the alkyl halide and the alcohol. Alkyl halide and the alcohol is the product. These are the two products that we obtain. But if we are using excess of this hydrogen halide, then the alcohol can further react with hydrogen halide, and as we have already discussed, in case of alcohols, the reaction of alcohols with hydrogen halides gives us the alkyl halide. So if we are using excess of hydrogen halide, then we'll be getting two molecules of alkyl halides, and if we are using the limited amount of this halide, halic acid or hydrogen halides, then we are going to obtain alcohol and the alkyl halide as the products in this reaction. Okay, now if we talk about the alkyl aryl ethers, in which we have one R group is alkyl group and another is the aryl group, okay, aromatic group. Then in this case we are getting phenol and an alkyl halide. Okay, so in case of alkyl aryl ethers, the products are always phenol and an alkyl halide, and we can never obtain an aryl halide and an alcohol. Okay, that seems to be the other possibility. We can that seems to be the possibility, that is, we'll be obtaining like this plus what do you call it, this alcohol. This is not the possibility in this particular reaction. We are always going to obtain the phenol and the alkyl halide. This is an example in this reaction. Okay, so an aryl halide ether will always produce phenol and an alkyl halide, never an aryl halide and an alcohol. This is because, why? Because we rarely say nucleophilic attack in an aromatic ring, because the aromatic ring is electron efficient, means it has lot of electron density present on the ring, so it cannot act as an what you call as the nucleophile, because it's full of, it has lot of positive charge, negative charge on its ring. Okay, so it mostly shows us the electrophilic aromatic substitution reactions. That is why in this case we are also only getting the alcohol and the alkyl halide in this particular reaction. Okay, so similarly we can have some cyclic ethers also, which are readily cleaved by these hydrogen halides. Okay, for example, if we take an example, this is an example of tetrahydrofuran. Okay, this is an ether, cyclic ether. Cyclic ether in many organic reactions we'll be seeing that this tetrahydrofuran is used as a solvent. Okay, we have already discussed about it. So when it reacts with hydrogen halide, okay, it can react with hydrogen bromide or hydrogen iodide, okay, at a particular temperature, that is 373 Kelvin. Then there is this ring is opened, okay, this ring is opened, and we get the dihaloalkanes in the reaction. We get the dihaloalkanes, and as in this reaction we can see, if we are performing this reaction with hydrogen bromide, okay, if we are performing this reaction hydrogen bromide, then the ring will be opened and we will be getting dialkyl halide, dihaloalkane in this reaction, dihaloalkane. Okay, this will be bromide, and the product, this is CH2 and Br. Okay, we can open this reaction. This is open chain product, and this is 1,4 dibromobutane. Okay, so this is the case of the cyclic ethers. If we have cyclic ethers, their reaction with hydrogen halides or halogen acids, these are also called as halogen acids, at a particular temperature results in the opening of this cyclic ether, opening of this ring to give the dihaloalkanes. Okay, as we have seen this as an example. Okay, now ethers, if we have ethers with two different alkyl groups, here we have shown as an example. This is an ether in which we have in the previous cases we have shown these were the examples of what you call as symmetrical ethers. This is an example of asymmetrical, or in which we have ether has two different R groups. Okay, this dash R dash is a different alkyl group, and this is the different alkyl group. In this reaction also we get different product. Okay, the product is different, and in these cases the alkyl halide is always formed from the smaller alkyl group. This is alkyl group. Okay, this alkyl group R dash in this case should be the smaller. It should be the smaller alkyl. It should be smaller alkyl group. Okay, this R, the smaller alkyl group will always form the halide. Okay, so in this case R dash should be the smaller one, and this should be the bigger alkyl halide. This is an example. In this case we have OCH3, and that is O is attached from one side, it is methyl group, and from another side it is ethyl group. So the halide will be formed by the smaller group. This is the methyl group, so methyl iodide will be formed in this case, methyl iodide. This is the alkyl halide that's formed from the smaller R group, and this bigger R group will form the alcohol. Okay, this is the alcohol, that is ethanol. Ethanol is formed by the bigger alkyl group. Okay, this is the order of reactivity of hydrogen halides, okay, or halogen acids. So the hydrogen iodides are what you call as this is the sequence that we should observe. This is more reactive than HBr, and HBr is very reactive than HCl. Okay, so the most reactive in this case is most reactive is the hydrogen iodide. Okay, so this is the order of reactivity of hydrogen halides. Okay, so this is actually based on the nucleophilicity. The order of nucleophilicity, the greater the nucleophilicity of the halide ion, more reactive is the halogen acid. And the nucleophilicity is this hydrogen iodide ion. Hydrogen ion is iodide ion is more nucleophilic than bromine ion, that is more nucleophilic than chlorine ion. So the iodine negative being this iodine ion being the more nucleophilic, that's why it is more reactive in this particular reaction. Okay, now let's talk about the mechanism of this reaction. Okay, see, we have three different cases which can arise, and we can these cases arise due to the different structure of the ethers. Okay, so these are different mechanisms that can be that this reaction can follow, that wholly and solely depends upon the type of ether we use. Okay, we can say the structure of ether, that depends on the structure of ether, and then also on the type of solvent that we use. Okay, so if we have an ether in which both the alkyl groups that are connected to the oxygen, they are primary. Okay, we have ROR, we have an ether in which both these R groups are primary. Okay, they can be different, but they are primary. If both are primary, then the reaction will follow the Sn2 mechanism, that is a concerted mechanism. Okay, substitution, nucleophilic substitution by molecular mechanism. And if one alkyl group is tertiary, or it is benzyl group, okay, one of the R groups is 3-degree alkyl group, or it is a benzyl group. Okay, it is a benzyl group, then the mechanism will be the Sn1 mechanism. Okay, it's tertiary, 3-degree, it's for the primary, it's for the 3-degree. And if we have a secondary, if one of the alkyl groups that is attached to the oxygen is the secondary alkyl group, then the mechanism that depends upon the solvent that we use. Okay, so the primary and secondary alkyl ethers react by Sn2 mechanism, while the tertiary and benzylic ethers, they cleave by the Sn1 mechanism. Okay. Now let's take the case first, case 1. So the case 1 is when both alkyl groups are primary. Okay, so the first case is that the both alkyl groups that we are taking are primary in nature. Okay, so let's take the example of the reaction between methyl ethyl ether CH2CH3, okay, and hydrogen iodide. Okay, let's take the example of this particular reaction. So in the first step, what's going to happen, this acid will break the hydrogen iodide that we are taking. It will break into its corresponding ions, and we'll be getting the proton and the I negative ion. Okay, let's consider this as the step 1 of this reaction. So in the next step, there is the reaction, there is the protonation of this ether, and in this step we get the protonated ether. Plus there is a reaction, there is a lone pair of electron present on this oxygen, and it will take the proton, and we will be getting CH3O. It's now CH2CH3. Okay, so this is the protonated ether that we have obtained in this particular step. Let's correct this first. Okay, so this is the protonated ether, and we have a positive charge on oxygen. In the next step, what happens, the protonated ether that we have obtained in this step, okay, it undergoes nucleophilic attack by the halide ion. In the next step, there will be the attack of this halide ion, that is iodine that we have taken in this case. This is the halide ion. Okay, now in this case, this pair of electrons will be taken by the oxygen in order to get stabilization, and the iodine will attack on this methyl group. Okay, and both these things are happening simultaneously. That is, there is a bond formation between the iodine, and this can be represented by this transition state. It is CH3. There is bond formation between iodine and CH3, and there is bond breaking or between carbon and oxygen. Okay, and we have CH2 CH3. So this is the transition state that we are obtaining, and the final product in the reaction will be getting CH3 methyl iodide and ethanol, CH2 CH3 OH. Okay, so methyl iodide and ethanol are the products in this reaction. So this is just simple mechanism, and this is Sn2 mechanism that it's following. Okay, when both alkyl groups are primary, the reaction mechanism will be Sn2 mechanism, nucleophilic substitution by molecular. Okay, so this is nucleophilic substitution by molecular. So this is followed when both alkyl groups are primary. This is the case 1 that we have studied. In the case 2, we have one of the alkyl groups is tertiary, or it is a benzyl group. This is the case 3, case 2. In this case, the reaction mechanism that's followed is Sn1 mechanism. Okay, nucleophilic substitution unimolecular. In the case first, in which we have followed the Sn2 mechanism, there was no formation of any type of carbocation, no possibility of formation of a stable carbocation. But in this particular case, there is a formation of a carbocation. How? Let's take the example. If we take an example, CH3 and then oxygen, and let's consider CH3. Okay, so one of the alkyl groups is 3 degree. This is tertiary alkyl group that is attached to this oxygen. In this case, there is a possibility of formation of a carbocation, a stable carbocation. So in this case, it will be formed. So in the first case, as we have seen in the previous reaction, there will be protonation of this ether, and we'll be getting CH3. Then this is the tertiary, and we have this protonated ether. The positive charge is on the oxygen. Okay, so in this case again, there is a possibility of formation of 3 degree carbocation at this carbon. Therefore this pair of electrons will be taken by the oxygen. Okay, and in this result there is the formation of methanol in this case. Okay, this is the first product of the reaction, and we'll be getting the CH3. This is the tertiary carbocation that we have obtained in this reaction. Okay, this is the positive charge that is present on the carbon. Okay, now in the next step, again the halide ion. Let's take the example of iodine. Again, I negative, because we have considered it as the most nucleophilic of all the halide ions. Okay, so it's going to attack this carbocation, and we'll be getting CH3. This is the product in the reaction. Okay, this is the product in the reaction. So we have obtained this alkyl halide, tertiary alkyl halide, and the methanol as the product in this reaction. Okay, so in this case we have one of the alkyl groups is tertiary, and another is the primary one. Now if one of the alkyl groups is benzylic. Okay, let's take the example. Let's take the example. If we have a benzylic group attached to the, this is a benzene group. Let's make it a clear one. This is a benzene and we have CH2O CH3. This is the benzylic ether, okay? This benzylic ether, aryl ether. Again, this will follow the Sn1 mechanism. There is again the protonation. That will be the protonation of the lone pair of electrons. Will take the proton. Okay, protonation of this ether will result in the formation of this particular product. This is the protonated product. This is the protonated product that we have obtained, and CH3. Okay, now we have positive charge on this oxygen. Now this is attached with this carbon as well as this carbon. So the lone pair of electrons, these lone pair of electrons will be taken by the oxygen. Why? Because again there is the possibility of formation of a stable carbocation. This carbocation, that is benzylic carbocation, that we are obtaining, that will be obtaining in this reaction is again stabilized by the resonance. Okay, so this pair of electrons will be taken by the oxygen. It will form, it will produce the alcohol. So in this reaction we will be getting CH3OH as the first product. Next we'll be getting the benzylic carbocation. This is benzylic carbocation CH, sorry, this is not CH3, this is CH2. Okay, this is CH2. So CH2 and positive charge on this. Now this carbocation is very stable. Again, as the tertiary carbocation is very stable, again the benzyl carbocation is also very stable, and this stabilization is due to the resonance of this particular ring. Okay, so this carbocation will be again attacked by the iodine, I negative, or any of the alkyl halides we are taking. Okay, this is an example here. So this will take, this will attack, this nucleophilic attack will be on this carbocation, and will be obtaining, will be getting CH2I. Okay, so this is the product that we'll be getting in this reaction. Okay, now we have case 3. Case 3. The case number 3 is that one of the alkyl groups is a secondary alkyl group. It's secondary alkyl. In this case, the reaction depends upon the product, depends upon the mechanism, depends upon the type of solvent that we use. Okay, so that depends upon the solvent, whether the reaction will proceed via the Sn2 mechanism or Sn1 mechanism. It will be decided by the type of solvent that we using. So we have two major types of solvents. One is the polar protic solvent, and another is the polar aprotic solvent. Okay, one is the polar protic solvent, another is the polar aprotic solvent. What is the difference between these two particular group of solvents? So in polar protic solvents, okay, these are capable of these type of, we have examples. Let's see first example. We have water, for example, H2O. This is the polar protic solvent. Okay, or we have an example of we can say, for example, we'll be taking ethanol, C2H5OH. Okay, these are two examples of the protic solvent. Okay, these polar protic solvents, they are capable of forming the hydrogen bonding. Why? Because these contain at least one hydrogen atom that is directly connected to the electronegative atom. Okay, as in this case water, we have at least we have at least one hydrogen. In this case we have two hydrogens. These are directly attached to the electronegative. So oxygen is more electronegative than hydrogen. Okay, so there is direct connection between hydrogen and the most electronegative atom. So this is an example. These solvents are known as the polar Protic solvents. Or in case of alcohols also, we have this OH. Here again hydrogen, at least one hydrogen is directly attached to the oxygen. Okay, so these such type of solvents are known as the polar Protic solvents. And polar aprotic solvents contain no hydrogen atom that's directly attached to the electronegative atom, and therefore they are not capable of forming the hydrogen bonding. For example, we have acetone as an example. Acetone, this is acetone. In this case we'll be seeing that there is no connection between the hydrogen and any of the we can say the electronegative atom. Okay, so this is polar aprotic solvent. Now we have to just remember this thing. Okay, we have to remember some examples of polar Protic solvents and some examples of polar aprotic solvents. Then we will be done with that. Okay, if we have 2 degree if one of the alkyl groups that's attached to the ether, to the oxygen of the ether is 2 degree, and the solvent is polar Protic solvent, okay, then we'll be looking at the formation of the carbocation, formation of the stable carbocation. So there is a possibility, if there is a possibility of formation of the stable carbocation, then the mechanism followed will be Sn1 mechanism. Okay, and if we have polar aprotic solvents, in this case the less will be following the Sn2 mechanism. Okay, Sn2 mechanism. This general rule we have to keep in the mind. So if we have 2 degree alkyl group attached to the ether, then the solvent will decide the type of mechanism that's followed. So if the solvent is polar Protic solvent, okay, that is the in which the hydrogen is directly attached to the oxygen or any other more electronegative atom, then such reactions will follow the Sn1 mechanism, and there will be the formation of carbocation. Okay, and if there are polar aprotic solvents that we are using with these type of ethers, then there will not be formation of any carbocation. Okay, and the reaction mechanism followed will be the Sn2 mechanism. So these are the different cases of the reaction between the reaction mechanisms that are followed by the ethers. Okay, which we have to remember. We have to generalize the things. Okay, we have to remember the mechanism is very simple. We have to just remember the general rules for these reactions. Okay, and we'll be able to solve many problems based on this reaction. Okay, so in the next video we'll be discussing other chemical reactions of ethers.